Section P2 gets into something that you should also be very familiar with, properties of exponents. So in your notes, be certain to write an explanation of each rule and also an example of each rule. So the product rule. The product rule is, of course, when we are multiplying, and if the bases are the same, then we are going to add the exponents. And the base is never going to change here. So x to the third times x to the fourth basically means x times x times x, there's x to the third, times x to the fourth. 1, 2, 3, 4. So 1, 2, 3, 1, 2, 3, 4, 7 altogether, x to the 7. Exponents are nothing more than shorthand multiplication, which is why we have these properties and they're going to only apply when the bases are the same. Now, the second example here, the base is 3. The base stays the same. Keep the base. I'm multiplying. Remember, multiplication can be shown with the dot or with parentheses. And if I'm multiplying and the bases are the same, I'm going to add those exponents. So 2 plus 4 is 6. 6 minus 4 is 2. Basically, 4 and a negative 4, they cancel each other out. And we're left with 3 squared. And you can leave it as 3 squared, but that's very simply simplified to 9. That's the product rule. When the bases are the same and we're multiplying, add the exponents. Next is the quotient rule. The fraction bar is indicating division and it's a quotient. If we were to write out x to the 10th over x to the 4th in an expanded notation, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. And we're multiplying all of these together. Hopefully I wrote 10. 1, 2, 3, 4. So think about it. What is actually going to cancel here? X over x is equal to 1. That's an identity. That's why if we multiply by the identity, we don't change the value. That's how come we can just cancel. That's 1. That's 1. That's 1. That's 1. 1, 2, 3, 4, 5, 6. 6 powers of x remain, which is, of course, exactly what we would get if we subtracted those exponents. 10 minus 4 leaves 6. So quotient rule. Once again, when the bases are the same and you're dividing, subtract the exponents. Subtract the exponents. Now, let's take a quick look at 3 to the 4th over 3 to the negative 2. Once again, the base will not change. The 3 is staying the same, just like the x stays the same. The base really never changes. If the bases are the same and we're finding a quotient, we're going to subtract the exponents. 4 minus negative 2. 4 minus negative 2. Minus a negative, of course, is plus a positive. We end up with 3 to the 6th. So 3 to the 6th is a pretty large number, so we're just going to leave it 3 to the 6th. Now, something else to point out here, and you learned this in Algebra 2, there's also another way that we could deal with that negative exponent. If a base has a negative exponent, we can reciprocate it to the top. So basically, 3 to the 4th times 3 to the positive 2 over 1. If we flip this 3 to the negative 2 up to the top, the exponent does become positive, and then it becomes a product rule rather than a quotient rule. However, we still get 3 to the 6th, and we will leave it that. I guess we'll simplify it. My calculator's right here. 3 raised to the 6th is 729. 729. There you go. Power to power rule. Power to power rule. A power being raised to a higher power. And normally if we have a power to power rule situation, there's normally parentheses present. So think about what this means. This means z to the 5th raised to the third power, which means z to the fifth times z to the fifth times z to the fifth, 5, 10, 15, which we could have very easily gotten just by multiplying those powers together. So if a power is being raised to another power, this is the time to multiply the exponents. Multiply the exponents. Now, in the second example, remember 10a cubed, the quantity to the fourth power means 10a cubed times 10a cubed times 10a cubed times 10a cubed. So, of course, that's expanded. If I were to apply the commutative property and the associative property to regroup and change order, I could change it to this. 10 times 10 times 10 times 10, a to the third times a to the third times a to the third times a to the third. So what we've really got going here is 10 to the fourth times 3, 6, 9, 12, a to the 12. So I'm pointing this out, hopefully it's quite obvious, that everything inside of the parentheses is getting raised to the fourth power, the 10 and the a cubed. So we have 10 to the fourth, that's a 1 with 4 zeros behind it. That's 10,000 a to the 12. Power to power, multiply the exponents. Now notice that the base stayed the same in the first example, and the variable base stayed the same in the second example, but this is a coefficient. And the coefficient 10, which is the number in front of that variable, is getting raised to the fourth power, and it does change. 10 to the fourth is 10,000. All right, 0 as an exponent. 0 as an exponent. If we have 0 as an exponent, what does that mean? Well, let's take another look at what we've got here. This is a product. And we have bases that are the same, therefore we should add the exponents. 2 plus negative 2 is 0. What does that mean? Well, let's take a look at something that maybe we're a little more familiar with. 4 to the fifth over 4 to the fifth, which means 4 times 4 times 4 times 4 times 4 over 4 times 4 times 4 times 4 times 4. And if we think of this in terms of reducing a fraction here, cancel, 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 cancel. If everything cancels, is it just gone? No, it's equal to 1, which hopefully was obvious all the way back here because this is 4 to the fifth being divided by itself. And any number divided by itself is going to be 1. And I mentioned the brief reminder that a negative exponent really just needs to be flipped. So if we have 3 to the positive 2 times 3 to the negative 2, if we were to put that over 1, we could just flip that 3 to the negative 2 to the bottom, and it would become 3 to the second over 3 to the second, which of course is a number over itself, 9 over 9, which is 1. So 3 to the 0 is actually equal to 1. If you have 0 as an exponent, you have a value of 1. Anything to the 0 power is going to be equal to 1. One last quick note here, and this is just another example of why anything to the 0 power is 1. Here are ascending powers of 2, and let's evaluate them. 2 to the first is 2, 2 squared is 4, 2 to the third is 8, 2 to the fourth is 16, 2 to the fifth is 32, then 64, then 128, then 256, and so on. So powers ascend forever. The powers of 2 are an infinite set. So if we can ascend forever, we can descend. So let's start descending here. So 32 divided by 2 is 16. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. I just drew my comma backwards. There we go, 1. So if we are descending our powers as well, then 2 to the 0 is going to fall in line there. We can keep going. So, all right, the next one will be 2 to the negative 1. So 4 divided by 2 is 2. 2 divided by 2 is 1. 1 divided by 2 is 1/2. We can keep descending here. 1/2 of 1/2 is 1/4. Now, what I would love to point out is the relationship of 1/2 and positive 2. Their exponents are opposites, but 1/2 and 2 are actually reciprocals. Same thing again if we look at 1/4 and 4. Again, reciprocals, but yet 2 to the negative 2 and 2 to the positive 2 have exponents that are opposites. So this is just another reminder of why anything to the 0 power is 1. It's going to fall as 1 in every expansion of powers. Powers of 3, powers of 5, powers of 10, whatever. So anything to the 0 power is 1.